Okay. Alrighty. Hi, everyone. So I'm Lyndon. I'm here to talk to you about how to build a debugger using Cassette. I'm an RSE at Invenio Labs. This isn't really work. You've got to have hobbies. Yeah. Before I start, a quick thanks to a bunch of people. People are very helpful. It's great. So what is MagneticReadHead? Basically, MagneticReadHead is a debugger that works by instrumenting your IR code. So it creates, it modifies your code to include the required debug annotations and then compiles it with the standard Julia compiler. We can contrast it to Debugger.jl, which is the Julia interpreter, and is thus, well, different. So you might ask why I want to do this, and the answer is, when I started it, we didn't have a debugger, and I thought, Revise and Cassette together, that seems like I could probably make a compiler out of that. Debugger out of that. And so I started playing around, and this is kind of the result. It's worth noting about the code base size. So MagneticReadHead, under 900 lines, didn't have to write Cassette, that already existed. Only 200 lines are kind of difficult. Whereas for Debugger.jl, they had to do an awesome amount of work, and it's really cool, but, they had to do it. I'm far more lazy. So you might think about performance. So this is a benchmark, same one that Tim showed in his talk a few days ago, although he didn't show the benchmark. And this is what it looks like. So the green line is the native, normal Julia performance if you're not doing any debugging. The orange line is MagneticReadHead, and the blue line is Debugger.jl, with no debugging being done, but just running the debugger through it. So by compiling your debugger, you can get some not so bad speed. However, it should be noted the performance of debugger is quite complicated. So notable thing for MRH, it has to recompile everything it touches the first time. And if you edit lots of things, it has to recompile everything you've edited. Not great. Furthermore, the kind of instrumentation we do, it utterly destroys SIMD and breaks CPU pipelining potentially. I've been told that maybe we can tell LLVM to fix this for us, but that's to be done. Also, some kind of insane performance black holes exist when it comes to compile time. So this is a fairly simple function. It basically just hangs when you ask MagneticReadHead to go through it, because turns out that involves recompiling an amazing amount of the standard library. I think it's not hitting any actual compiler bugs, so I can't rule it out because it doesn't terminate compiling. And the reason for this is because it massively increases the amount of lowered code generated. You go from 160 IR statements to 20-something thousand, and the compile time increases quadratically with the length of your IR. So yeah, it is quadratically with a very small number in the front, so it looks kind of linear or better. But when you're up at 20,000, it's not good. Yeah, so about performance, we've got Debugger.jl, which works really cool, but it does have this runtime overhead. And we've got MagneticReadHead, which has this, well, it's quite fast, but very significant pile time overhead, really problematic. But we're all working on this, and we can certainly solve this. We have this capacity, and I think we can end up saying with the best of both worlds, or everything being fast, because it's what we do in Julia. So let's think about how we're going to build a debugger. So what do we need? We need to go through the code, and we need to check when we're running it. Should I be breaking here? So I call some should break function. And if we do want to break here, we need to call a break action, which is some function to do some, well, things you want to do while you pause your code. If not, we want to just keep running our code. So to do that, we can imagine that we'd like to modify our code to just actually insert these function calls in between every IR statement. Thus the large increase in the number of IR statements, because you have to add this everywhere. So what does a should break do? We want to check if we're step next or step out, some kind of stepping mode that says that you should break all the time. And we want to check our current location, which is the method, the module, whatever, against the list of breakpoint rules that we defined as some structure by calling set breakpoint. and the break action. So we want to start up a REPL, substitute in the local variables so you can query those, and make sure we can call like set breakpoint, because after inspecting this one, you want to set another breakpoint. So make sure you can do that. And we also need to handle like entering stepping mode or exiting stepping mode. So what does it need? We need to know where we are in the code so we can like print the current line so you know where you're up to. We need to know the current state of all the variables because that's why you're debugging. Obviously there's something wrong in your state or you wouldn't have, well, a bug. We need a way to interact with them, and we need to be able to set and remove breakpoints because, well, yeah, you're being to change as you're debugging. So a quick intro to Julia IR. So multiple layers of representation. We start with the source code, you parse it, you get the AST. You lower it, you get the untyped AR, that's what we're going to talk about mostly. You specialize it, and you get the typed AR, which then goes through optimization. CodeGen makes LLVM, and eventually you get assembly. So the untyped AST, not going to go too many details because Tim covered it the other day, but basically we take the AST and we linearize it into a list. You can call it like, it's kind of an abstract syntax list. So yeah, it's quite easy to read, but it's not so easy to work with. So how does Cassette work? So Cassette is not magic. Cassette just uses kind of standard stuff that the compiler was already doing. We have generated functions, which we all know can return an expression. They're also allowed to return a code info, which is the representation of, well, IR. And the nice thing about code info is we can ask the compiler for the code info for any method. So we can then mutate that code info to return new functionality. So this capacity lets us build a whole pile of tools. It's very flexible, it's quite nice. Yeah. So we can imagine implementing, this is like a manual Cassette pass done by hand. We've got a generated function called rewritten. It's just grabbing the code IR, iterating through it, looking for function calls. If it sees a function call, replace it with a call to call and print, which is going to print out the function, and it's going to, well, then call the function. And then we just continue going, and we're going to return that code info object, which will then just run like a compiled thing. So that works. You can do that, and look, now here we are printing out some all the stuff that was inside our function. Cool. Now, if we didn't do call and print, and we said something called like overdub, which does the print, and then calls rewritten, which does the rewriting, then we get to rewrite the functions that our function calls using the same method. And so that's how you can build Cassette. It's how you can build an IR tools Dynamo. Ask me about Arborist. It's cool. So we're going to make our first debugger. You might want to like, this should be considered with reference to the Cassette doc. So I'm not going to fully tell you, but basically our first debugger, we're just going to overdub functions that we want to debug. So on a function call, we're going to do the thing where we check if we should break and take a break action, and always call the functions. It won't let us put breakpoints in between lines, but it will let us intercept every function call. And since everything you do in Julia is done by calling a function, that's pretty powerful. And we can avoid touching IR, which hurts me. So that looks something like this. I haven't put in the actual thing, but you see we've just got an overdub, pass in a context, find out what method you're in, and yeah, then recurse. So that works. You can do that. That's completely fine. And obviously with some small changes, that could become a debugger. So to generalize that, we want to be able to set some breakpoints, delete the breakpoints, have stepping modes, and improve the user experience, have an actual REPL. So I'll show you quickly some of what you have to do for that. So this is kind of the details of the next slide. You don't really need this. Oh man, no examples. Well. Here we go. So debugger bits. So to do the instrumentation for this before, we just need a call to, well, set breakpoint, looks like this. It's a function, it calls eval to actually create the overdub, and that does what we were for. To remove the breakpoint, we've got this macro called undeclare, which takes an expression and does delete method, thus removing the method so the breakpoint won't be hit. And yeah, that works. You can set a breakpoint and it appears, and you can delete it. You can trust me on that works. Yeah. So yeah, other bits. So you can write a REPL fairly easily. The instructions in the name. It needs to read, evaluate, print, and then loop. And that looks like this. The only thing that's kind of not in the name is you need to substitute in your local variables, which you can do fairly easily, but it's walking that expression tree and substituting in your variables for the ones you captured from your context. You can use the code info and the code logs, which are part of the IR statements, to look up where you are in the code and vice versa. Or you can use codetracking.jl if you don't want things to go bad with Revise, and it also has a bunch of helpers for this. Stepping mode is kind of painful, but you need to have a set of logic, which is basically a state machine for, like, if the stepping mode was step next, and I've already done the step next, what should I do now? You have 4 states. It's fairly easy. Going out has 16 states, and it reduces to about only 3 logical expressions, but like working those out, not trivial. It's probably worth drawing like a state machine and then reducing it. I didn't, but I should have. You can take a look at the MRH code and you can find it's fairly simple, really, once you've worked it out. We're now going to take a short break. Okay, and we're back. So, a second debugger, because one debugger is not enough to show people how to build. So what we want to do is to modify the code directly, so actually insert the statement so we can do it on every line. So to do this, we need an IR pass. So that's much like we did at the start, except we're going to use Cassette to help us because that's easier. You don't run into quite so many corner caches that I hand-waved over before. Yeah, so to do this, we need to basically use the reflection object which Cassette gives us when we do a pass, and we must return a code info. So the reflection object tells us the method and some other stuff, and the code info, which is the one we want to modify, which contains a bunch of useful fields like slot names, which we're going to need to name all our variables, the line info that we needed to find out where we were, and of course the code that we're going to modify. We're also going to use a little helper. Cassette will recurse into everything unless you wrap it up in a overdub. So just to keep the code in the next slide short, I'm going to go call expression, which is going to insert an expression to call with overdubbing disabled. So for each statement that we encounter in the IR, we want to check, based on where we are in the method, what the original statement was before we instrumented. Should we be breaking here? If so, we're going to create a variable as an array of symbols to hold the names, another one as an array of, anything to hold the variables. We can do some stuff for each slot to actually check what variable's there, which I'll show in a bit. And then we're going to call the break action, which is going to open up our REPL debugger. And after that, we're going to actually do the statement. So in untyped IR, it looks like this. So first, we're going to call the should break. Then we're going to check what its value was. So the index is this line. SA value from this line. If it isn't set, then we go to down here. And if it is set, then we're going to declare that variable via the shorthand of getIndex, because that's one, it's easier to type than define a constructor. But yes, that line creates us our variable name slot, and this line creates us our variable slot. And then we will do the stuff I mentioned before and eventually call into the debugger, passing in our variable name slot and our variable slot. So then for each statement, we want to check, is the variable defined? If it is defined, we're going to put into a list of our variables that are currently defined, and if not, well, we won't. Because you can't put non-defined values into a list, given that they're not defined and it's not legal to put them inside objects in Julia. So we need to make sure everything's defined before we actually do that. And we have to do that for every single slot, which is why we get just that many more statements, because you have to keep checking our slots to make sure everything's defined every time we are, because you don't know what path's been traversed through the code to get here. So in the IR, this is not incredibly bad. Check if it's defined. If it's not defined, then we're going to jump over these ones. Otherwise, push it into our lists. Yeah, so that works. You can do that. You get a thing that looks like a debugger. But there is a problem. You can't just call isDefined whenever you want. You see, there's a rule which says that things have to be declared before you can check if they're defined. And the variables that are inside this inner function aren't declared until you get into the inner function. And yeah, so that kills the optimizer. You get this really fun error. Basically, that -1 is just a sentinel value that occurs when the optimizer did something that it didn't expect to do. So solving this is left as an exercise to the reader. I have a way to do this that doesn't work, but is not terrible, and I have a way to just ban any slot if it hit this new var node, which works, but now you can't see those variables anymore. It's fiddly. If you actually do solve this as the reader, please make a PR. That'd be great. So I thought I should talk about how to make your instrument debugger, or your cassette code in general, not incredibly slow. So when I first made MagneticReadHead, it was like 10,000 times slower than it is now. It was way slower than Debugger.jl, which was done. So yeah, you can do better than I did. So we all kind of know about hot loop optimization. Make sure the code in your hot loop is fast. The hottest loop you can imagine is every single statement in your code. If you make those slower, then everything gets slower. The second hottest loop is every single function call in your code. Don't make these things slow. So one thing, it's really elegant to implement the state machine I mentioned before to decide if you're going to step or you're going to continue or you're going to whatever. You can implement that as dispatch. It's dynamic dispatch based on like singleton values, but it's in normal Julia code, that's kind of fast and it's very readable. Yeah, you do that every function call. Faster is to do a if condition based on enums. So that got me about an order of magnitude. Don't store a running dictionary with all your variables. So rather than like trying to check if things are defined, you can just, every time someone assigns a variable, put it into a dictionary so you always got a reference to it. If you do that, you don't get the, you don't get that out of bounds error I got before because you're doing fairly simple code that only uses variables after they're defined because you're adding them to a dictionary after they're used. But yeah, that means you allocate every single time an assignment is done, which is slow, and allocating. Don't call methods to get the method. Tim found this one too, I think. Yeah, calling methods takes like a full microsecond, which is a lot if you do it every function call. Once you're inside the pass, it's already been done once and at compile time, so you can use it then. Until then, you need to structure your debugger so that you don't need to know the actual method you're in and can use some other information to know about where you are. Play around with no specialize. So no specialize stops the compiler from specializing on types, which it kind of tends to do most of the time. That's a feature. But often inside the debugger, there's not really any benefit to specializing because you're always doing the same thing to the code no matter what the input type was, especially if it's like a tuple type or a function type. It just has innumerable types just for like something which for your purpose is the same. Inline your overdubs. I found this out like a few days before the thing. Got a nice order of magnitude. You can inline your overdubs. Always inline your overdubs. It's just really good. So the other one, what can I do about those compile times? They're pretty big. So we had this slide before. We got those n slots times n statements things after we've instrumented it. Far too many, got to cut down on them. So, one, we don't have to instrument every function. So MagneticReadHead always has a set uninstrumented. In Debugger, I think they call this compile. And that just says we're going to leave that alone. But it means that if you've got, say, set uninstrumented map, then you won't get any debugger in the function you're mapping onto. So it's a bit sad. New idea is to have this semi-instrumented thing, which you can't break inside this, but you can break in my children. So I'll only instrument it enough to tell it to recurse into my children. It still means recompiling everything, but you're not adding as many statements. A nice side effect of this is you can also like just kind of ignore some modules which you're not interested in. Someone was saying to me they'd like to not see cassette when they're debugging their code. So they'll be like, set semi-instrumented, cassette. And then you only have to see things that are not, well, that are part of what you expect to have errors in them. You can generate less code by not instrumenting each slot as hard. So to be precise, this is how many statements we have. It's 4 times the number of slots plus 5 times the number of statements. So if we stop building the list of slot names, because we can just declare that kind of once at the start and work it out because the slot names are in fact in our code info object. We just need to then mask them out later for the ones that aren't defined. We can cut out a whole 1 plus n slots times n statements, which I found that to be like fairly solid speed up in my quick play around with this. But still not enough to actually compile that function I gave at the start. That still takes longer than I expected to. You can be kind of smart and not bother checking if something is defined before it has been used, since it can't have been, well, if it's been used, it's been defined, and if it hasn't been used, then you don't need to check it. And so you can do this kind of thing. You can not check it after it's been used, since now you know it has been defined. And if you understand the flow of code in your function you're analyzing, you can emit a bunch of these calls, which can, between the two of them, save you 2 times the number of slots, times the number of statements there, which is a nice fraction to cut off. But the analysis is kind of hard to do on code info. So to solve this, I kind of want to look at IR tools, which has a bit better tooling for looking at the structure of code, which might help analyze this better. We can also just only instrument each line once. So one line contains many statements. And if we only instrument them once, then we can cut out like down to this order of magnitude, where n lines is much more than n statements. And you can get more speed up that way. And it's probably easier for the user to use anyway because they wrote their code onto logical line structures and probably weren't interested in each individual substatement in the line because, it's kind of, if they have bugs per line, they can always rewrite it. And that's what you have to do in most debuggers that I've used in like MATLAB or C# anyway. So I think that's fine to do this. And again, that big cut down on the amount of code you're generating. And finally, we could sort out that thing where Julia doesn't remember stuff you've compiled in the previous Julia session. Since most of our time, MagneticReadHead always instruments the same code in the same way. So if we can store that between Julia runs, then you only have to instrument like the standard library once, and then next time it'll be fast. That'd be great. We could also ship a system image, which has had this done, but I think creating that system image would take like heat death of the universe amount of time to create right now, so I'd rather not. A lot of these things that we can do to decrease our compile time do come with kind of the downside that we are in fact running compile time logic to decrease our compile time code on the hope that the compiler spends less time compiling it. So there is a trade-off to how much time do you spend analyzing your code to make the analysis easier on the optimizer. You have to work that out. Stuff left for MagneticReadHead. There's some bug squashing that has to be done to try to like not have that out of bounds error, but also fully instrument all your variables. Want to rewrite in IR tools because more ability to analyze structure, and I theorize that have some evidence that Cassette being a bit more powerful than IR tools, sometimes the compiler doesn't like it as much, and some things don't cache as well as they do in a simpler IR tools Dynamo. That also could maybe a little bit of work in Cassette to work out what's going on, but it's quite hard, and you need to debug Cassette's code and work out what's happening is quite difficult. Cthulhu is about the only tool I think that can like work out what's happening inside Cassette. It's quite unfun. And more alignment with Debugger.jl, or alternatively start looking at how we can move some of this kind of tooling into Debugger.jl so we can have the best of both worlds. We don't want these like infinite compile times, but we do like these like really fast runtimes. They're quite nice. yeah, that's about it. Yeah, I suggest taking a look at MagneticReadHead. It's only like 855 lines, so it's quite bite-sized. It's not actually as hard as it sounds. You too can build a debugger. Mike?
So about the instrumentation you have to do, I wonder if you considered lifting set of breakpoints into the type system and then using that to decide what to instrument at compile time.
So Mike asks if I wondered about lifting the, deciding if I should break into the type system so I can use that to decide at compile time. And I thought about this at one point. It basically means a lot of things, like at very least your stepping instruction, you can move that into your context type in Cassette. But it's quite, well, it has to become, you need to start redeclaring your context type every time your stepping mode changes, and that's an allocation, which tends to be really bad. I removed all the allocations from that as part of making it faster. And it would also mean we'd have to compile the code not once, but 4 or possibly 16 times, depending on how much we need to consider the type information. So I don't think I like it. Yeah.
I just like to say really elegant work, and thank you so much for undertaking this. I definitely think there are opportunities for sort of using the sort of best things from both of them and the thinking about the problems that we both face to try to figure out a good solution forward. And one of the things that I found myself wondering about from our very difficult performance problem, and I'm wondering actually if it could help you with your difficult is defined problem, is kind of stealing Cassette's more sort of generic notion of a tape recording. And I wonder what your thoughts are on whether we could get good mileage out of some of these things, for instance, as a potential means to solve your is defined problem, to actually take some risks with regards to how well we document program execution state as we're stepping through it, and essentially instead document where we are and what values were produced, and then try to sort of unwind some of that information and assign them to actual variable names at the stage where we're presenting the results to the programmer.
So you mean using some of the tooling from Julia Interpreter to help analyze the code structure?
Or whatever, but yeah.
Yeah. I think analyzing the code structure in general, via whatever means there is a good idea. Because, well, cutting out those statements is important. Another interesting thing that's kind of also between sharing stuff is there's vinyl.jl, which is kind of Cassette, but implemented on the interpreter. So you could use MagneticReadHead on the interpreter, which would be interesting, at least. And I think it would allow at least this same code to, well, run with different performance characteristics. Yeah. Vinyl needs a bit of work to actually pull this off, I think, but it's mostly there, I think. Cool. If there's no further questions, talk to me about Arborist.